Hello everyone, my name is Joseph Lizier. I'm an ARC DECLA Research Fellow and Senior Lecturer at the University of Sydney. This presentation on pointwise partial information decomposition using specificity and ambiguity lattices is primarily about work carried out by my PhD student Connor Finn. The work is currently under submission. Hopefully it will be published by the time you watch this video, so you can Google for the title and hopefully find it then. Information decomposition has been a very hot topic in information theory about complex systems in the last few years. The goal of information decomposition is to identify redundant, unique, and complementary or synergistic components of the mutual information from a set of sources about a target. We can illustrate this simply with examples of two source variables and one target. The goal is to try and predict the target using those source variables. And what we want to do is decompose the mutual information from either those sources individually or jointly about the target. And we can look at this equivalently using equations or using a diagrammatic approach. Using the diagram, we can see that we consider the mutual information from each individual source to the target being composed of a redundant component, information that we could get from either source about the target, plus a unique component from each source that the other source does not provide. Once we put the sources together, we also get a synergistic or complementary information piece from both sources that we couldn't get from either source alone. We can see some canonical examples of what we mean by these three components of mutual information. Unique information, for example, is provided here by source 1 about the target when source 2 provides no information. Obviously, those probabilities should be a half, not a quarter. A canonical example of redundant information is here, where both sources provide the same full information about the target. The canonical example of synergistic or complementary information is, of course, provided by an exclusive OR operation. But these three kinds of information could be provided in general at the same time. For example, in the AND operation, there is some redundant information in the sources providing a 0. There's some unique information in these situations here where only one of the sources provides a 0, and there's complementary information in the one outcome in the target where we need to know both sources to know we're going to get that result. What we need to understand then is that we have three unknowns here. We have three equations, but four unknowns that we want to solve for. So we can't get this decomposition using traditional information theory alone. Paul Williams and Randy Beer really laid the groundwork in this area by providing an axiomatic framework called partial information decomposition, where we can try and decompose these components over an arbitrary number of sources. They laid out three basic axioms for what the redundancy should look like, and if we can solve for redundancy, we can solve for all of the other components. The redundancy should be symmetric under permutations of the sources. It should be monotonic. As we look at more sources, the amount of redundancy amongst those sources should be non-increasing. And as a boundary case, the self-redundancy for only a single source should be the mutual information from that source. When we have those three axioms, we get what we call a redundancy lattice, which is a structuring of how the redundancy amongst these source components forms a hierarchy. It's very simple to understand in the two-source case. The redundancy between sources 1 and 2 is lower in the hierarchy. It's a component of the redundancy of source 1 alone or source 2 alone, both of which are components of redundancy when we consider source 1 and 2 jointly, which is what we mean with these curly braces. We're looking at joint sources. It's much more complicated when we go to three sources. We get lots of more complex terms. For example, here, if we look at the redundancy between source 1 and sources 2 and 3, taken as a collection. But we won't really go into that in this presentation. We'll just focus on the two-source case. Importantly, while we have the lattice, we know how the redundancies should be structured. We still need a measure of redundancy. The axioms aren't enough to lock a measure in. And there is still no acceptable definition of redundancy or either the unique or synergistic components that is applicable to more than two sources and or gives us returns what we can accept is the same information being called redundant about the target at the same time. Now, to look at what we mean by the same information at the same time, we need to turn to pointwise information theory. The pointwise information was derived by Fano many moons ago, although it's not that particularly well known these days because most people use the average mutual information. The pointwise information is looking at the information shared by two specific events, X and Y, which co-occur. So not looking at the average information held by the variables about each other, but specific events of those variables. And we can look at that as a difference in the posterior probability of Y given X versus the prior of Y, or equivalently the other way around about X. One feature of the pointwise mutual information that is very different to the average is it's not non-negative. We can have negative values where the posterior probability drops below the prior, and so we call that when one variable is misinformative about the other. Our first contribution here is to say that we should be able to do information decomposition pointwise for each realization. And we think that this approach will allow us to more properly identify when we hold the same information at the same time, because we're talking event-wise or point-wise. So here we've just rewritten the same equations but on a point-wise basis. We should be able to take expectation values over these local redundancies, unique and complementary terms, to get back to our average values of each, and this should recover then the average information decomposition. One of the key reasons we want to do this is to be able to solve for situations like this one, which we call pointwise unique, where we can very clearly see when we should and should not hold the same, that the information should be identified as the same or not. In this example here, we have situations where in each configuration, one of the sources fully decodes the target when we have a 1 or a 2 in that source, whereas the other source, which provides a 0, gives 0 information about the target. And we can see that when we write down the mutual information terms from single sources or jointly. We suggest that in this situation, there should be 0 redundancy, because one of the sources tells us nothing, the other tells us everything. And if we can write that down, we can solve for the other unique and complementary terms and get on average half a bit uniquely from each variable here. Let me re-emphasize, in each row, one of the sources tells us everything, the other tells us nothing, and that's why we see this, why we postulate this alternating pattern of unique information here. The issue that we have is that all of the currently suggested methods for redundant information give the answer of half a bit in this situation, which is not equal to what we're postulating here as 0, because in each situation we see nothing held redundantly in the same event. The problem is that all of the current approaches don't look on a pointwise scale, and that's what we want to revisit information decomposition to do. So we suggest that to get a pointwise, we started by suggesting that to get a pointwise partial information decomposition, the very same 3 axioms should apply on a pointwise scale. But we can't really get anywhere with that approach because of the fact that pointwise mutual information is not non-negative. Then we're not going to get this monotonicity property, and we won't have the lattice holding for us. So that's not really quite the way forward. That still doesn't give us a clear definition of redundant information if we just try and apply these axioms directly on a pointwise scale. So we need to rethink the approach. To do that, we go back and think about what exactly is pointwise information here. As I said before, it's basically about the surprise of the posterior compared to the surprise of the prior regarding the target. We realize that this change from the prior to the posterior is ultimately derived from exclusions in the probability mass space. So let's have a look at what we're calling probability mass diagrams here. We can draw up for the event space T and S1. We can draw a probability mass diagram. On this side, we represent the lengths here are proportional to the probability mass that we have for each event. So here, event T and S1 are the events that occur. So we have some mass associated with event T and some mass associated with the complement of that event. And same for S1. we can now partition with event T and S1, or T and the complement of S1, and the same for the complement of T with S1 or the complement of S1. So if we read off that the event S1 happens, what we can do is we can exclude any probability mass associated with the complement of that event. And then we can renormalize that to look at the posterior probability of each outcome T given S1. To look at the pointwise information here, what we're going to do is we're going to compare the probability mass associated with T from our prior with the renormalized posterior probability of T given S1, and that will give us our pointwise information. It's important to note that we can get the same pointwise information from two different sources with different exclusions. So here we've got source 1 and source 2, which offer different exclusions in the probability mass space, yet we get exactly the same pointwise information value. So the pointwise mutual information is not injective, and we suggest that we need to understand whether exclusions are the same or not before we can declare that we have the same information or redundant information provided by those sources. To do that, we started looking at what are the kinds of exclusions that we can get, and we identified two types. Firstly, purely informative exclusions, where the complementary event to S1 that we observed is all associated with the complementary event to T. What happens here is we get a purely positive information provided by S1 about T, and the size of the positive information increases with the size of this exclusion. In contrast, if the exclusion provided by the event S1 is all associated with the event T that happens, we actually get a misinformative, a negative information from S1 about T, and the magnitude of that negative information increases as the size of this exclusion. But in general, we can have both of these exclusions at once. What we want to be able to do is to split the pointwise mutual information in two components associated with these exclusions, a positive component and a negative component. And what we did was to prove that if we want these components to increase monotonically with these exclusions, and we want to have a source chain rule, the only way to write down these components is as a Shannon information content of the source or a conditional Shannon information content of the source given the target. Now we know, of course, that we can decompose the pointwise mutual information in this way, but it's non-trivial to prove that this is the only way to do it that satisfies those properties. Of course, we're talking here about a directional decomposition from the source to the target. We know that the pointwise mutual information itself is not directional, but the decomposition of it is, and that's important. So we call these components specificity and ambiguity. Specificity here because here we're talking about how specific the source is about what might happen versus how ambiguous it is. Returning to our previous example, we can now quantify how these exclusions are different. We get the same pointwise mutual information from source 1 and source 2 here, but because the exclusions they provide are different, we see differences in the specificity and ambiguity component of both. So now we can start to look at how we can use this to provide a pointwise partial information decomposition. And we suggest that this should be done separately for our sources for the specificity component, R plus here, or the ambiguity component, R minus. What we can do is directly map these first three axioms straight across to the specificity and ambiguity. And this yields for us two separate redundancy lattices, one for each component. We no longer have a problem with negative components. Now our components are non-negative in each of the specificity and ambiguity spaces. So we have the lattices, but we still need a measure of redundant information on each lattice. To lock that in, we need one more axiom. We suggest that should be that in the pointwise spaces, the redundancy components should depend only on the size of the informative and misinformative exclusions. Just the size, not about whether they're overlapping or not. This is akin to an important assumption of previous work from Niels Birchinger and company, which suggested that you cannot infer complementary information or synergy without knowing the full distribution. here in the pointwise space, we're suggesting that you cannot go up to that higher order complementary information term. You can only go up to that higher order complementary information term when you know whether those exclusions overlap or not. But at the level that we're inferring redundancy and unique information, you just need to know their size. The only sensible thing to do under that axiom is to take the minimum across all the sources. So we can define the minimum specificity, we can define the redundant specificity as the minimum across all the sources, and the redundant ambiguity as, again, the minimum ambiguity across all the sources about that target event. Once we have that in place, we can come back and revisit our examples. Coming back to the pointwise unique information, if we decompose this now using our new measures, we get exactly what we hoped for. That, in net, the redundancy in each row is 0, the positive component cancels with the negative, and we see only unique components from each of the sources being non-negative in net. Importantly here, I've been talking about the nets. You will notice that we do see a redundant specificity and a redundant ambiguity, which we didn't predict before. We did predict that the net was 0, but in not seeing that there were two components, we didn't know that we would have these components that cancel out. So that's quite interesting. We can also look at the classic XOR case. And of course, in net, we get the classic result, complementary information or synergy being 1 bit. But again, what we can now reveal is that there is a piece of redundant specificity and a piece of redundant ambiguity identified by these measures which cancel out in net. There are quite a number of further properties here which we don't really have time to go into in this presentation, but you can read more about these in our paper. Importantly, we can provide an interpretation of these components in terms of Kelly gambling, which is a classic information theoretic approach to returns given optimal betting strategies. For example, we can reveal that the difference in unique information is simply the difference in the winnings of the two players in this approach. Importantly, our approach is generalizable beyond two sources, which is something that the field of information decomposition has been struggling with. It is able to do that in part because we have a target chain rule in net. So not on the individual specificity and ambiguity components, but when we put them back together, we have a target chain rule, which is if we can decompose our target variable into two targets, the redundancy for the first target and then the redundancy for the second given the first comes back to the redundancy about those two targets in net. That is particularly important because it means that our approach is the only one that provides a consistent decomposition of the 2-bit copy example, where we look at decomposing information from two independent bits, source 1 and source 2, about their joint variable. Because information theory is consistent under relabeling of any variable, we can actually relabel this target variable in several different ways and decompose it via a chain rule in each of those ways, and we should have the same decomposition whichever way we decompose it. Our approach, as the only one having a target chain rule, is the only one which will do that consistently. Finally, there are many echoes of the intuition we've provided here behind the previous measures from Birchinger and Company, Ince, Williams and Beer. What's different is that we've been able to apply that intuition in a fully pointwise manner and on a component-wise manner for both the specificity and ambiguity, and that's what allows us to go further than those previous approaches, for example, in having a target chain rule. At the back of our presentation, we provide a set of references that we've talked through today. In particular, the paper where we're presenting these results. As I say, it's currently under submission. It should be available soon, so please do Google the title and you'll find it. I'd also like to advertise our special issue on information decomposition at the HB Journal, which you can get to via this link here. That special issue, again, most of the articles are out. There are a few more coming out hopefully in the next few weeks, and by the time this presentation hits, you should hopefully be able to see almost all of them. Thank you for your time, and if you've got any questions, I'm looking forward to addressing them in the forum.